This is 40 Days of Chemistry Part 12, this time looking at 9.3.2, the second part of 9.3.2, this time looking at acidic oxides and soft drink. Now, one big part of this focus area was looking at acidic, amphoteric and basic oxides and the periodic table. Now, the first thing is acidic oxides. Acidic oxides are oxides that react with bases, and they're also oxides that produce acidic solutions when dissolved in water. And typically they're non-metal oxides, such as carbon dioxide. Carbon dioxide reacts with water to produce carbonic acid. It can also neutralize bases. Now, just be aware that there are some non-metal oxides that are neutral, such as carbon monoxide and dinitrogen oxide, and also the higher the oxidation number of the element in the oxide, the more likely it is to be acidic, such as things like NO2 is more acidic than NO and N2O, for example. Just also be aware that the noble gases don't form oxides at all, so that's an example of a non-metal that doesn't form acidic oxides. Now, basic oxides, they're oxides that react with acids. They're also oxides that produce basic solutions when dissolved in water, and they're typically metal oxides, such as calcium oxide here. It reacts with water to produce calcium hydroxide, which is a base. It can also neutralize acids, such as sulfuric acid. Now, the amphoteric oxides react with acids, and they also react with bases. They form salt plus water with acids. They act like a typical base with an acid. They like acid plus base goes to salt plus water. When they react with bases, though, they form complex ions. And the examples of the amphoteric oxides are things like lead oxide, zinc oxide, aluminium oxide, tin oxide, and beryllium oxide. And there's a little periodic table down here which has been labelled with different sorts of oxides. And just in general, as you move from left to right across the periodic table, you go from being basic oxides to amphoteric oxides to acidic oxides. And that's the general trend across the periodic table. The next part of this focus area is looking at the soft drink equilibrium. This is the first time we encounter the Chatelain's principle. We've already done a big talk on the Chatelain's principle with the Haber process. This is going to be quite quick. There's a whole lot of ways you might see this soft drink equilibrium written. Essentially, though, what it is, it's carbon dioxide reacting with water to produce carbonic acid. That carbonic acid is a weak acid, and therefore it partially dissociates into the bicarbonate ion and hydrogen ions, and that again can then dissociate into carbonate ions and hydrogen ions. But they're all equilibrium reactions, and they're all exothermic. So going from left to right, they are exothermic reactions. You can also write them down as Bronsted-Lowry theory, donating protons reactions if you wish as well. But as long as you're aware, whenever you see any of these sort of reactions, it's the carbonic acid or carbon dioxide equilibrium. So how does that relate to soft drink and the Chatelain's principle? Well, because they're all equilibrium reactions, that means the Chatelain's principle applies. We know that temperature, pressure, and concentration all affect position of equilibriums via the Chatelain's principle. So because they're exothermic, if we raise the temperature, that means the reaction shifts to the left and makes the carbon dioxide less soluble. If we lower the temperature, that's going to favour the exothermic reaction. It's going to shift the equilibrium to the right and make the carbon dioxide more soluble, which is why you keep your soft drink in the fridge, to keep the carbon dioxide dissolved in solution. Pressure, if we raise the pressure of the gas, that's going to drive the carbon dioxide or drive the reaction to the right and make the carbon dioxide more soluble. If we lower the pressure, such as say opening the bottle, it's going to make the carbon dioxide less soluble because the reaction is going to shift to the left. And that's why soft drink goes flat when you open the bottle or open the can, because you've lowered the pressure and therefore the carbon dioxide becomes less soluble. If you increase the carbon dioxide concentration, if you can somehow remove carbonate, such as precipitating it out, or remove the hydrogen ions, such as by adding a base, in theory that makes the carbon dioxide more soluble because the reaction shifts to the right. On the contrary though, if you add carbonate ions, or if you add acid, or if you can somehow remove carbon dioxide gas from the atmosphere, that's going to drive the reaction to the left and therefore make the carbon dioxide less soluble. Our soft drink experiment was all about measuring the mass change when soft drink was decarbonated. To measure mass change, just be aware you've got to measure the mass before opening and after the carbon dioxide has been lost. So if you're asked to write a method for this experiment, you must mention you measure the mass before we open the can and the mass after you open the can. But how did we account for evaporation loss to make our experiment valid? We used a control which had water only, and we could measure the mass change of that control and take that evaporation loss away from the total loss of our normal soft drink can. But how do we know all the carbon dioxide has been lost? How do we know when to stop the experiment? Well, there's two things here. First of all, there's no way you can remove all the carbon dioxide anyway, and we just have to make an assumption that the maximum carbon dioxide was lost. So why can't we remove all the carbon dioxide from the can? Well, because we said before, it's an equilibrium, and as long as there's carbon dioxide in the atmosphere, there's always going to be some carbon dioxide dissolved in the soft drink because of that equilibrium reaction. How did we try and remove as much as we could? We opened the can, which is reducing the pressure. We took it out of the fridge and brought it to room temperature, so we raised the temperature. Both by lowering the pressure and raising the temperature, we're driving the reaction to the left, making the carbon dioxide less soluble. We just had to observe that there was no bubbling and we left it for a long period of time. We just had to assume that all the carbon dioxide was lost. So why was there a mass loss full stop? It's because carbon dioxide escapes from the can. Carbon dioxide's a chemical, it's got mass. we can calculate the volume of carbon dioxide that escaped, because we can figure out the number of moles of carbon dioxide lost based on mass divided by molar mass, and then figure out the volume of carbon dioxide escaped, which is volume equals number of moles times molar volume. The last thing in this particular focus area is gas volume calculations. We've done quite a few of these. You need to be aware of the gas volume formula. The volume of the gas equals the number of moles times the molar volume. Molar volume is dependent on temperature. The lower the temperature, the lower the volume. So 1 mole of gas occupies 22.71 litres at 0 degrees and 24.79 litres at 25 degrees. There was a question in one of the trials which had kelvins rather than degrees. You need to be aware that 0 kelvins is the same as minus 273.15 degrees Celsius. So 0 Celsius is the same as 273.15 kelvins, and 25 Celsius is 298.15 degrees Celsius. And the last little tip here, don't forget to convert gas volume to litres if the gas volume is given in mils.